Enzo and Larry asked me to give an initial talk. Several purposes. One is to kind of get us on the same page, and this talk is deliberately dreaming. If you're, the technical community folks tend to not be dreamers, or we are in our own private way, but we often don't speak about our shared dreams. So I'm going to try to paint a picture of what the future might be for SRF thin films. It may not be true, but in the spirit of Enzo's last presentation, the job of making that transition from reality, from dreams to reality, is, if it's going to happen, it's us. Okay. Of course, the principal drivers for SRF technology, the applications are particle accelerator field. There are a few other applications, but the serious support comes from particle accelerators. And what really matters is vanishingly low surface resistance at fields that are then useful for accelerating beams. So then we have to look to what serves the customer's needs. So we're going to do a little bit of strategic market analysis, if you like. Of course, it may be obvious, low losses and high fields are what's needed, but really it's low integrated system cost per unit acceleration. So I want to force us, even though we may be very narrowly focused on materials, we're in the context of applications where it's the integrated system costs that really make a system attractive or not. So that means including the resonator system, the cryostat, RF drive system, and even the cryogenics. In the future, the great majority of SRF accelerator applications will be CW. There are a few very notable exceptions. People dream about the ILC, but I'm not going to talk about that. And very dominantly, realizing the lowest surface resistance is what's imperative. It trumps all else. High gradients, especially in CW applications, are completely useless unless the surface resistance and thus the cryogenic load is commensurately low. So then, what credible opportunities might there be to make a dramatic impact in the future? So I'm going to try to paint a picture. So what sets the stage for SRF thin films? For the customer, only the price of units of acceleration matter. Everything else to them is just details, and we're just the equivalent of refrigerator salesmen. Okay? As a guide, as a tool, heuristic tool, I'm going to ask you to keep us from dreaming too far off the real plane. I created a model of system cost for 100 megavolts of CW LINAC, suitable for accelerating 1 milliamp of beam. Now, different applications have lower current, some have higher current, but this is in the middle of the road, and I think it may serve as a useful guide for us. For some applications, this may be very close to the application needs, some compact FELs, for example. Others, it may just be a building block in the way to something much larger. So I tried to build a model to link RF surface resistance, accelerating gradient, cryogenic, and RF capital, and even a 10-year operating cost that would be required to provide 100 megavolts of acceleration. If you increase the beam current, at the first order, that only adds to the RF power. All the other costs stay the same. So where are the opportunities? Let's dream a bit. And we'll dream, in my dream, that we're limited by BCS. You'll work out the details, so that's true. Okay, here's the landscape at 1300 megahertz. And because I'm at Jefferson Lab and the world is at 1497, do I have a pointer? I don't have a pointer. Shucks. Okay, you can see on the curve, this is BCS with some kind of generic parameters for niobium, niobium nitride, and niobium 310. Oh boy. High tech. Okay. Temperature, surface resistance, and I picked 4 values of surface resistance, 6 nanoohms, 38, 80, 170 nanoohms as some representative values. Then you'll see why. I'm going to use them in some contours in a minute. And Okay. This is where the JLab upgrade spec is, 38 nanoohms. Thank you. Okay. So niobium nitride, niobium 310. Okay, the cost of 100 megavolts, of course, depends on frequency, temperature, accelerating gradient, with the particular material you use, the geometric factor. I still have to juggle three things. And R over Q of a particular structure. I take, in order to be anchored a little bit in reality, I take, and that's because I wouldn't know the numbers, I take the Jefferson Lab upgrade numbers as a benchmark, and we scale up and scale down from that. Okay. Here's some assumptions in my model. Real estate is free. Cryostatic, the static cryo loads are linear with active length. RF power is constant. Controls and distribution scale linearly with length, basically number of components. Cryo module cost is proportional to active length. That means once we know what to do, cryo modules don't cost any more to make them better. Cavities now $100,000 a pop. You can do an awful lot for $100,000 if you know exactly what you want to do. I think our problem is we don't know exactly what we want to do. Cryo capacity is designed to the target load. Capital cost and operating efficiency. I talked to Ralgani, who's arguably one of our cryogenic experts at Jefferson Lab, who's done a lot of different system designs to look at costs, and he has a very conservative cost model. I use that to include what it would cost to provide 4K or 2K cryogenics and operating costs. I assume we're BCS limited, and for simplicity, I say the cavity geometry is a constant. It would actually be tailored. Then I do that and I look at, this is what 100 megavolts CW LINAC costs with those assumptions to build it, and 10-year operating costs for a 2 Kelvin system. As a function of these four values of surface resistance. Okay, it's obvious that surface resistance is a dominant factor, right? 6 nanoohms and the world is it's flat. This is $10 million. This is cavity gradient, 20 up to 120. This square is the CBAF 12 GeV upgrade, 20 megavolts per meter, design surface resistance 38. We tend to do a little bit better. 29 is BCS. But then we're dreaming, right? I would say dream number one, that's by nomenclature, D1. Dream number one is 650 megahertz niobium film at 2 Kelvin. Okay? It would be quite a bit cheaper than a system that at CBAF. Maybe half the cost in increments of 100 megavolts. Dream number two, niobium nitride, SIS structure at 2 Kelvin. 20 megavolts per meter. You need that with niobium nitride most likely. But half the cost before you even do any structure changes. Okay, dream number three, niobium 310 at 2 Kelvin. Okay, why not 50 megavolts per meter? Sit out here producing quite a bit less heat and quite a bit less cost than the CBAF upgrade. There's three dreams. How about at lower frequency, 650 megahertz? Here's BCS, same set of curves. I make a little note. I don't know where to put magnesium diboride on these plots. If anybody does, please tell us this week. There are hints, but there's nothing very clear whether it sits up here or sits down here or sits up here. We shall see. Okay. So at 4.2 Kelvin, the world looks a little differently. Again, I put on for reference the heat, the cost for the system at CBAF. but I add 4 more dreams. 650 megahertz niobium nitride at 4.2 Kelvin is right here. Half the cost. Going to go down, if you do the same thing in niobium 310 at that level, and be conservative, don't even require BCS, but 6 nano-ohms you see is a nice minimum. Things happen, if you could get to 6 nano-ohms, the reason things get flat is that as the gradient goes up for a constant 100 megavolts, your static heat loss, you win by being shorter and going up in gradient. So that's what makes this cost flat, as opposed to just assuming that you have runaway costs as quadratic losses eat you up. Okay. Sixth dream, 1300 megahertz, niobium 310 at 4.2 Kelvin, 60 megavolts per meter. Do you want to do that? Do you want to make it real? And then there are some applications, Tsuyoshi, that would really love to have 100 megavolts per meter at affordable heat costs. So this may be quite a bit cheaper, but surely we need a complex structure that really pushes the field up. None of this is real today. What are you going to do to make it real? So I summarized some of these dream objectives. Caveat emptor. Let me point out R1 reference, that's reality today, $10 million for an incremental 100 megavolts. This is the CBAF upgrade. One dream, niobium, the cheapest niobium solution, half the price of CBAF acceleration is niobium film, BCS limited to 650 megahertz. If you could do that today, you have lots of people knocking at your door. The first incremental application of a superconducting insulator structure might be niobium nitride at 20 megavolts per meter on 1300. You could even retrofit some existing cavities if you could do this, if you knew how to do it. Lots of people would be happy because you cut the dynamic load down by 70%. That's big bucks for applications. Okay? Then you start dreaming a little bit further. 50 megavolts would be very attractive for compact FELs. Maybe even ILC might be credible. And fourth generation light sources. Big structures. At 4 Kelvin, it would be nice to have a driver for accelerator-driven systems. If you could do the same thing with niobium 310, an even cheaper driver. A cheaper ILC, that maybe it's actually buildable. How about commercial terahertz sources? Many applications for material interrogation, industrial processing. And then at the highest end, compact portable interrogation systems used for security and trying to find fissile materials in shipping containers. So there are, to take a lead off of Enzo's comment, there are a lot of social, very broad social values underlying these items, whether they're green energy production that's needed for the next 3, 4, 5 centuries, or tools for doing research that just cannot be done any other way, whether it's for materials, whether it's biological materials. These are tools for that kind of research or basic research. So I don't know what motivates you, but I hope that some of these dreams maybe you want to share. Because if it's not going to happen without you doing it. I'm done.